So we have two talks today, two speakers. The first one will be Jim van Orman from Case Western, and that will be followed by a talk by Rebecca deGraffenried. And she's really from Honolulu, but as of the last 2 weeks, she's in Bochum now. So let me just begin by introducing Jim. Now, if you have been doing things related to diffusion at all, you know Jim, because he has done so many different things related to diffusion that no matter what you work on, you're likely to have encountered his work in one way or the other. But very briefly, to give a little bit of his background, Jim did his PS in Florida State University in Tallahassee, and then went on to do a PhD at MIT with Tim Grove, which he got in 2000. After that, he has largely been, did a postdoc in Carnegie Institute in Washington. And since then, he's been faculty at Case Western University. He's had visiting positions in different places in Lyon in France or in Zurich. And he has had a number of different awards. I'll just say that pick one out as a highlight, which is the Clark Medal of the Geochemical Society. So today he's going to talk about modeling closure temperature in isochron systems. And when we are planning this lecture series, and I asked Jim if he would like to talk about something, and when I said that we'd like to have discussion going, Jim came up with this idea, and that I think is a topic that will lead to discussions right away. So without much ado, I've stopped sharing here and asked Jim to take over. Jim, all yours. If I can get out of this here. Okay, I'm out. Yes, so it's all yours, Jim.
Okay, I'm sharing screen. Well, thank you, Shumit. Why is this not working? Here we go. Sorry, let me get this going. Okay. And okay. So thank you, Shumit. I emailed Shumit yesterday to say that I was a little worried about this talk because it's been a really crazy week here with the first week of classes and COVID, students
recording in progress.
Becoming infected. And he's don't worry about it. What we really want to do is, I'm hearing a really big echo for some reason. There we go. What we really want to do is generate discussion with this. So this talk may be a little bit rough, but I'm going to try to be clear. So what I'm going to be talking about is applications of diffusion to radiometric dating. And of course, this is important in, all across geology. And one of the most important things, if you measure radiometric date, is what does that actually mean? Is that the formation of a rock? Is this a flow, or is it sometime later because of resetting due to diffusion at high temperatures? And one of the most important techniques for obtaining radiometric ages are isochron systems. And I'm showing an example here. This is for rubidium strontium. Rubidium-87 is the parent isotope, and it decays to strontium-87 with a long half-life, billion years. So what happens with the way the isochrons work is you have various different minerals or portions of a rock that have different rubidium-strontium ratios in them. The idea and the assumption is that they begin in isotopic equilibrium so that they have basically the same ratio of strontium isotopes, all of these different reservoirs at the beginning. And then as decay proceeds, the compositions, the isotopic compositions of those follow this isochron. And due to decay, and you can measure the age if you know the decay constant based on the slope of that isochron. what happens is that diffusion at high temperatures will tend to bring the isochron back down so that the different minerals in the rock are trying to get back to isotopic equilibrium, and that will tend to reduce the age. So so one way that this has been addressed, for some reason this is not working. Okay, sorry. So there are other, I just wanted to introduce this as well. Isochrons are not only used for long-lived radioisotopic systems, but they're also used in planetary sciences for looking at meteorites using radioactive isotopes that were present at the beginning of the solar system, but have such short half-lives that they're now extinct. So one example of that is aluminum-26, which has a half-life of about 700,000 years. So it goes extinct very early in the history of the solar system, but it was around at the beginning, and many meteorites that are young enough that sort of stopped being active early in solar system history still preserve evidence of having the aluminum-26 around. And it's essentially the same idea, except here, instead of plotting the parent, 26 aluminum is all gone, you plot the stable non-radiogenic isotope aluminum-27 over a stable non-radiogenic isotope of magnesium. And then this is the magnesium-26, the deviation of the magnesium-26 from the normal isotopic ratio here. And what this gives you is not exactly the age, but it gives you the apparent initial aluminum-26, aluminum-27 ratio, which, if you know the starting ratio at the beginning of the solar system, which is done by measuring really the oldest stuff that we have that closed very quickly, this can give you very precise ages with really good resolution. But the same kinds of things go on here, where you have diffusion acting against the to shift this isochron and potentially affect the ages. So, well, one way that the primary way and with dating that has been used since it was developed in the early 1970s by Dodson is this model that is pretty familiar to, well, it's familiar to anyone who works in these kinds of things, metamorphic rocks or radiogenic systems. So the Dodson closure temperature model is one where you have a single mineral, single reservoir that has, in this case, radioactive isotopes in it that are decaying to radiogenic daughters. And those radiogenic daughters can then diffuse out of that system into an infinite sink. So that's the assumption in the Dodson model, that there's an infinite sink out there for these daughters to diffuse to. Nothing happens with the parent in this model. It stays put. It's happy being in the mineral. And so really it's only the radiogenic daughters that are trying to diffuse out into this infinite sink. And what was really new about this Dodson model is that it considered diffusion during cooling, during slow cooling. And it assumes that at high temperature at the very beginning, all of the daughter is lost. So you can see that. This is from Dodson's original paper, I believe. I pulled this off the internet, but I think it's from that paper. So this is the ratio of daughter to parent. And initially, all the daughter is lost. So the daughter to parent ratio is 0. Temperature is high enough that everything is lost to the sink. But then as temperature cools, gradually daughter starts to be retained. And eventually, as you get out to very low temperatures, diffusion shuts off altogether at low temperatures, and all of the daughter that has been produced in that time interval is retained. So the closure temperature is defined as, if you take this low temperature part of the curve and extrapolate that down and get an apparent time that refers to, based on that trend, where the daughter was 0, that is the apparent starting point. And the temperature along the cooling path that corresponds to that time is the closure temperature. So this is a really powerful model that's been used ever since the 1970s for all kinds of things. And it has a lot of advantages. You can define the closure temperature. It's a very simple model in terms of the radius parameters, the temperature dependence of the diffusion coefficient for the daughter isotope in the mineral. It's a function of the size of the grains, how far atoms have to diffuse to get out to this infinite sink. There are different shapes that can be considered, simple ones, sphere, slab, cylinder shapes, and then it depends on what the cooling rate is, which governs how much time is available for diffusion to happen. But when we look at isochron systems, there are some issues with using the Dodson closure temperature model. There are special cases where it is a really good representation, but in general, with isochron systems, there are multiple minerals involved, not just a single mineral diffusing out to an infinite sink necessarily, but there are multiple minerals that are exchanging radiogenic daughter isotopes, and none of those might be an infinite sink for them. Another thing that comes into play, not for long-lived radioactive systems, but for meteorites, when looking at extinct nuclides, which have short half-lives, one of the assumptions in the Dodson model is that decay is slow, and then it really doesn't matter. You can use the same closure temperature whether there's decay or not. But for many of these, decay might not be slow compared to cooling, and that could have an effect on the closure temperature that actually applies to the system. It may differ from that you model with the Dodson model. Another is that for some isochron systems, both the daughter and the parent could diffuse during cooling, because in general, during cooling, the partition coefficients of the elements, the parent and the daughter elements, change. And there might be significant not only loss of these radiogenic daughter isotopes to different minerals in the rock, but the parents might diffuse as well. And that can affect the isochron age, particularly if the parent diffuses faster than the daughter, which sometimes happens. And another one that we've just started working on recently, and as far as I know, there isn't a published literature on this yet, although I could be wrong. We can talk about this in the discussion, is that diffusion could produce isotope fractionation of the radiogenic daughter isotopes from reference daughter isotopes, which could also affect the isochron ages. So these are the things that I'm going to talk about in this talk. And I'm going to examine these in terms of a simple numerical model, a little bit more complicated than the Dodson model, but as simple as it can be to address these kinds of issues, because of course, there are a lot of complications that can happen in real rocks with complex geometries and so on. So in this model, I'm going to be considering two minerals with spherical grains that are exchanging with each other by diffusion. So here, what's represented here are two mineral grains, same mineral, that are interacting with a second mineral. So mineral 1, mineral 2. They can have different sizes, they have different diffusion properties, they have different partitioning properties for the parent and the daughter isotopes. And so in most of these, I'll just be considering the daughter isotope, but the parent isotope can also, it's also possible to consider the diffusion of the parent isotope as well. So one critical assumption that is really one for convenience, it may or may not apply in various rocks, but it's one that's been used. I think the first time this assumption was used that I'm aware of is by John Euler looking at stable isotopes of oxygen, but I'm not sure that that's the case. But this is the assumption that there's a medium around the minerals that is very fast diffusing, that can accommodate the fluxes that are coming out of or into the different minerals, and basically keep everything in equilibrium at their surfaces. So all the minerals, all the way around them, are in equilibrium at their surfaces. And this makes things much simpler to model, because instead of considering complicated 3D geometries where it depends on what a mineral is in contact with, they're all assumed to be in communication with each other in terms of their chemistry. And so they can be modeled simply as spheres, which is essentially one-dimensional diffusion. The diffusion and the partitioning properties between the two different minerals in general are different. So those can vary. The proportions of the different minerals can vary. So here you have a lot more of mineral 1 than mineral 2 in this little cartoon that I drew, for example. And it's possible to consider different types of cooling histories, although everything I'm going to show today assumes that the temperature history is the same as what's considered in the Dodson model, where the temperature, the cooling is 1 over temperature versus time. It's linear in that. And you can consider different initial conditions. So this simple system, there are differential equations that describe the diffusion, the partitioning, and the radioactive decay. And they're solved using a Crank-Nicholson finite difference scheme. This is done in MATLAB in the code that I developed for this. And radioactive decay and diffusive exchange are happening simultaneously in this model. They're solved at the same time. Okay, so what I'm going to focus on is, first of all, the effect of a finite sink. And what I'll be considering here is that, there's exchange between two different minerals, and this medium out here is not an infinite sink. In general, I'm considering it to be very small, like a grain boundary, infinitesimal volume, so that there's not any significant amount of radiogenic isotopes in the medium. So we're just looking at the exchange between two mineral systems. And what happens if the sink for the radiogenic daughters is not infinite, as it is in the Dodson model? What if that's a finite sink? What does that do to the closure temperature? Another thing that I'll address very briefly, I'll just have one slide on this, is the effect of fast decay. So if decay is fast compared to the cooling, what does that do to the closure temperature? And finally, I'll present some work that is in progress that PhD student Jiwa Chung is working on, has been working on for the last year or so, and that is the influence of diffusive isotope fractionation on the isochron ages. So hopefully this will generate a lot of discussion. So the first thing that I want to present, and this is focusing on the role of a finite sink, is some work that I did recently with Thorsten Kleine's group, where they were looking at the palladium-silver system. This is an extinct radionuclide system in iron meteorites. And so they generated some nice isochrons on these, and I got involved to try to help understand what the meaning of the ages that they get from those isochrons are, in terms of what point in the cooling history of these iron meteorites do the ages correspond to. So in the iron meteorites, the metal is the primary repository of radioactive palladium-107. And the primary sink for the daughter isotope, silver-107, is troilite, iron sulfide mineral that's present in virtually all iron meteorites in some abundance. So it tends to partition silver into it much more than palladium, and it's the opposite in the metal. So there are some complications in these iron meteorites that I haven't even talked about yet. You can see this nice Widmanstätten texture due to the exsolution of two different metallic phases, a BCC phase that's poor in nickel and an FCC phase that's rich in nickel. At high temperatures in general, there's just one FCC phase, and the exsolution happens at relatively low temperatures. But there are complications that happen here in terms of, okay, where is the closure of the palladium silver system relative to the exsolution of the metal? I'm not going to address any of that here. This is just considering that there's a single metallic phase, but there are some additional complications that can happen with the exsolution of the metal. But I'm not going to talk about those today. What I'm really going to focus on is just what is the role of this troilite sink in terms of, it's not really an infinite sink, even though it partitions silver into it. Troilite in general is a minor phase in these iron meteorites, and it may not be, and in general usually is not, an infinite sink for silver 107. Okay, let me move on. So this is what's motivating this work. This is an example of an isochron that Thorsten Kleine's lab generated for Cape York iron meteorite. And so troilite is down here, kind of anchoring the isochron. It has very little palladium in it. And then the metal has high palladium and low silver. And so this defines an age. Well, really it defines a palladium 107, palladium 108 ratio, which can then be translated into an age given the initial for the solar system. So this is what we're trying to understand. So first we did some, I ran some benchmark tests. So basically I'm looking at grains of metal and grains of troilite. The geometry in this system is a little bit, kind of tricky. It's probably not perfect. The model that I'm using is not perfect for describing what's going on here, but basically we're taking the average distance between troilite grains and translating that into a metal grain size in order to model this. So here's an example for 5 centimeter metal grain radius with initial cooling rate of 250 degrees per million years. And here I'm just, testing, okay, how many radial steps in this finite difference model are needed where I have an infinite, troilite reservoir effectively in the model, and comparing to the Dodson model. So if I use enough radial steps, say 1,000 or more, then the closure temperature that I get from the model, and I'll explain more about how that is done, I think, in the next slide. It's within a degree of the Dodson closure temperature. And, depending on the computer I'm using, with this many steps, I can't remember exactly. It takes, maybe not too long to run a closure temperature simulation, like half an hour maybe. But as more and more steps are added, this might take overnight or something on a laptop that I'm using. Okay, so the way the closure temperature is defined, very similar to the Dodson model. Basically, in the model, I have a 2-point isochron. I have a metal with a particular palladium-silver ratio that's based on the partitioning properties of the metal with the troilite, and a troilite grain with the same thing, and those form a 2-point isochron. And then the time that is recorded by that metal troilite pair, either the bulk metal or with some distance in the metal, is then taken from the model isochron, from the compositions of those metal and troilite, and the time that corresponds to is then corresponds to a temperature in the simulation, and that is the closure temperature. This is the apparent time recorded by the isochron. The temperature of the model at that time is the closure temperature. So I'm just showing this to show that the closure temperature actually, and Dodson modeled this later, I believe in the 1986 paper, which I haven't looked at in a really long time. But the closure temperature is a function of, where in the grain that is, undergoing diffusion is, are you referring to? And one thing I forgot to mention here is that this system is simple in one way, and that is that troilite has really fast diffusion properties. Actually, the only thing that has been measured is iron, not silver, but iron diffuses much, much faster in troilite than in metal. And so that makes the system pretty easy. The closure temperatures here don't depend on the diffusion properties of the troilite, assuming that silver is somewhat similar to iron, both are cations. And in troilite has very high vacancy concentrations. And so that makes diffusion very fast. So that's the assumption here, is that, that silver diffuses similarly to iron, and it can basically equilibrate, so it doesn't matter. So looking at the metal, though, as you get very close to the troilite, the metal has lost a lot of the silver isotopes, so it has a relatively low closure temperatures because it's continuing to exchange with the nearby troilite. Whereas you go farther and farther away, it's not, the composition of the metal is not changing. So you can integrate over this, and most of what I'm going to show in this talk is the integrated closure temperature. If you just homogenize the whole mineral or integrated the composition over the whole grain, what would you get? But you can also look at it as a function of distance. And Kleine's group actually did some things with this where they looked around the troilite at different radii, and that can be used to get better refinements on what the cooling rate of these meteorites are. But I'm not going to talk about that today. The one thing that I really want to focus on here is this is showing different model results for different cooling rates. These are different curves for 10 degrees per million year cooling to 10,000 degrees per million year cooling, initial cooling rates. And as a function on a log scale of the troilite fraction. So if everything's troilite, this is an infinite sink. And these correspond to the Dodson closure temperatures in this case, because the diffusion properties of the troilite don't matter. So these are just like the Dodson model. But as in general, troilite is less than 10% of the iron meteorites. And you can see that this has a big effect on the closure temperature. And the reason for that is that if you have a finite sink of troilite, it's really easy to change the isotopic composition of the troilite. So if it's infinite, it just sits there in the same place as, no matter what happens to the metal and how much diffusion there is, it's just sitting there. It's got an infinite sink of silver. No matter how much silver 107 you diffuse in, it's insignificant. But if it has a small fraction, any little bit of silver 107 that diffuses out of the palladium is changing the composition, the isotopic composition of the troilite, and moving it up, lowering the slope of the isochron, and that results in a lower closure temperature because you're continuing to affect the isochron slope down to lower and lower temperatures, because it doesn't take, if it's a very small troilite fraction, even the amount of diffusion you can get out of the metal at quite low temperatures is enough to move the troilite and affect the age. So this can be a really, really big effect that really has to be considered. So if you have a system like this with a finite sink, you can't use the Dodson model because it will really strongly overestimate the closure temperature in that system. Okay, so this is moving to something totally different. And this came out, okay, this is looking at the effect of fast decay. So this is something that can be important potentially in extinct radionuclide systems where decay is much faster than it is in long-lived isotope systems like uranium lead, samarium neodymium, rubidium strontium, and so on, the ones that people who work on Earth systems are familiar with. But in these planetary systems, the early solar system materials where you're using some of these extinct radionuclides, it could be a significant effect. So this came out of discussions that I had with Eli Block and then Jiba Ganguly after I visited Lausanne a few years ago for a diffusion short course. I'd actually looked at this before, the effect of fast decay, but it kind of put it aside. And I've actually done that again. We did, I ran these simulations in collaboration with Eli and Jiba after the conference, and then it's a little bit more complicated than, too complicated to write a really short paper on. And so various other things have come up, and I just kind of dug this out because I think, it's pretty interesting, and I don't think it's been addressed in the literature. But this is looking at the effect of fast decay in these systems for different, each of these is for different kind of cooling rates and or diffusion parameter grain sizes. So but basically, I don't want to focus too much on that. But what's most important is here, where what's represented on this axis is the half-life of the radioactive isotope over the closure time, how much time it takes from the beginning, the high temperature part of the simulation, to the time of closure. And so if you're way out here, the half-life is very long compared to the closure time. And this is the situation that you'll have with basically any long-lived radioactive isotope system, where the half-lives are, on the order of billion or billions of years. Cooling is generally going to be, much faster than that for any geological sample that you have. So you'll have a really long half-life compared to the closure time, and it's not going to matter. So what's represented here is the closure temperature in the model system divided by the Dodson closure temperature. So if you have a long half-life, you get Dodson, and these are all for infinite reservoirs, so that it's comparable to the Dodson model. And but as you get down to shorter and shorter half-lives, the closure temperature starts to go up compared to the Dodson model. It's not a huge effect unless the half-life is really short compared to the cooling time, but it can be up to a 10% effect. It's not as big as the finite reservoir effect, but this can potentially be important. And basically what's happening here is that now early on in the simulation, basically if radioactive decay is very fast, then radiogenic daughters can build up in the source mineral that's enriched in the radioactive isotope much faster than diffusion can take them away. And so it's different than in the Dodson model, where basically the buildup, most of the buildup is happening after early on in the simulation. Radioactive decay is not so fast that it's overwhelming diffusion, but in this case, it is, even at these high temperatures, and then it freezes. So I don't want to say too much more about this because it's been a while since I've really looked at it, but I just wanted to show this as something that can be important in these extinct systems. Okay, finally, what I want to address is the effect of diffusive fractionation of the daughter isotopes on the isochron ages. And again, this is work that Jiwa Zhang is doing. So here is an isochron system with the parent to the reference daughter isotope and the radiogenic daughter to the reference daughter isotope. And what can happen is that you can have both chemical redistribution of the parent and daughter during cooling, and you can potentially have, due to that chemical exchange, you can have isotope fractionation that could could either make more steep or less steep the isochron. So basically, these effects result from temperature dependence of the partition coefficient between the minerals that leads to a redistribution of parent and or daughter during cooling. And in the case of the isotope separation, it's a result of both that and the dependence of the diffusivity of the isotope on its mass. So different isotopes of the same element have a dependence in general of the diffusion coefficient on mass that's represented here. So this is the diffusion coefficient of the light isotope divided by the diffusion coefficient of the heavy isotope. And in general, the way this is represented is in terms of the mass of the heavy isotope divided by the mass of the light isotope to a factor beta, which is just an empirical constant. In an ideal gas, this would be 1/2, beta would be equal to 1/2. But in minerals, that can vary between 0 and 1/2. And there are some theoretical considerations that can provide some guidance on this, but in general, we never have enough information almost never, to predict what this is. We wrote a paper on this several years ago. So essentially, this is almost always an empirical constant that we don't have a great theoretical understanding of. And we actually don't have very many measurements of it in the types of things that we care about. So this is a plot that Jiwa put together showing beta factors for various minerals. And really the only thing I want to show here is that there aren't a lot of data for us to base things on, but essentially, beta is always less than 1/2, but it's never 0. So at least in the things that we've measured so far. So these are for iron, magnesium, and olivine. Lithium and olivine has a little higher beta. This is work that Jiwa is working on now on calcium and enstatite based on modeling of that system and comparing it to natural samples. But what I want to show is that even if the beta is relatively small like this can potentially have a significant effect on some isochron systems. So what I will show here are some modeling that Jiwa has done recently on the samarium neodymium, long-lived samarium neodymium system in a system like spinel peridotite with orthopyroxene and clinopyroxene. So these are the model results over here. This is just showing the diffusion coefficients that the model results are based on. This is the mineral-mineral partition coefficient between orthopyroxene and clinopyroxene. The dashed lines are the equilibrium values based on work of Jan Liang's group at Brown. So what's happening here is that the partition coefficients of both the parent samarium and neodymium are temperature dependent, meaning that during cooling, samarium and neodymium will exchange between the orthopyroxene and clinopyroxene. Both will tend to move from orthopyroxene into clinopyroxene as cooling progresses. And then these are the model results for what the effective partition coefficient is. And you can see that it stops changing. And basically that's what's represented here. This is kind of the closure temperature for the partitioning in this system. But what happens, what we want to address is, okay, as samarium, particularly for neodymium, as neodymium is moving, the light isotopes of neodymium can move faster through the orthopyroxene to get to the clinopyroxene than the heavier isotopes. And that can lead to a separation of the radiogenic daughter from the reference isotope, and that can affect the ages. So how does that affect the isochron? So these are GWAS results for this for a particular cooling rate, 100 degrees per million years. I can't see the grain size here because it's, what is it, 0.5 millimeter. Anyway, so this is a particular example. And what GWA has modeled here is for different beta factors, different mass dependencies of the isotope diffusivity. 0 here, and these are the isochrons, okay, the 2-point isochrons between CPX and OPX at the time that closure happens for the chemical exchange. Okay, so basically this is sort of the initial place where the isochron is at the closure time. And what happens is that if beta is 0, you know, nothing much happens in terms of the slope of the isochron. But if beta is not 0, then there's a significant downward slope of the isochron. And so basically what that means is that if there is this diffusive fractionation during the cooling of the system, because neodymium is being transferred from OPX to CPX, and the lighter isotope 143 neodymium moves faster than the 144 neodymium, that leads to a lower 143, 144 in the orthopyroxene, because the 143 is able to more efficiently be transferred to the clinopyroxene. And that leads to a negative age at the beginning, which then has to be overcome by, you know, radioactive decay. So this can have, you know, even if beta is as small as 0.1 or less, this can tilt that initial isochron by what would look like, you know, 83 million years. So this can be a significant effect. And I am going to end the talk here, and hopefully we'll have some good discussion about this.
Thanks, Jim. Yeah, it's fascinating to see all the new factors that come up in looking at the Dodson equation, which you've now known for over 50 years or so. So I'll wait to see if I give people some time to type, things and to get into the chat so I can read them out. The thing that occurred to me listening to you speaking is that the meteorites give a very nice way of doing model tests, because once you get to terrestrial rocks, of course, the question that comes on top of all of these is whether diffusion was the thing that was controlling the exchange at all, and you know, the issues with water and dissolution and precipitation and whatnot. And I see some people, I don't want to put anybody on the spot here, but I see people names here where may have thoughts on the things. But while people are putting it together, maybe one question for you quickly, Jim. So the twilight example that you gave, do you have any terrestrial equivalents of that you think where that same effect might be applicable, where cases where the non-finite diffusion rates would play a role?
You know, I haven't thought specifically about that. I think in this samarium neodymium case, it's probably not a very big effect, although it could be. We haven't actually looked at that, at what the finite reservoir effect is there, because in that case, in terms of the samarium neodymium, well, let's think about that. Actually, I bet it has an effect if you were looking at something with garnet in it, because garnet would have a high samarium neodymium ratio, and there might not be a sink for the neodymium that is effectively infinite compared to garnet. So that's not something that I've looked at specifically, but I would bet that you'll see a significant finite effect there.
In eclogites, there are these famous garnet pyroxene negative ages, which I think may be related to that, because garnet and pyroxene would be definitely not infinitely fast things, and not a system where you should use Dodson to get a closure temperature. So the other work that I remembered listening to you was Gavin Jenkins, way back when, looked at the effect of modal abundances of biotite and plagioclase in the rubidium strontium system. So
Yeah.
He talked about that.
Yeah.
But while we've been talking, it's good because now I have a couple of questions from Igor. And so Igor, why don't you unmute and ask if there's something about the size of samariums? I can read that out, but if Igor can unmute himself and show himself.
Yes. Can you hear my question now?
I can hear you, yes.
Right. So I have questions. I have a total of 4 questions. So I start with the last one, which is on the screen. In the case of samarium and neodymium, samarium is smaller. So samarium will, if neodymium can diffuse at all, samarium will diffuse faster. So I'm not sure that the modeling of immobile samarium will give the correct answer about the delta T.
Yes, so in this case, the modeling is considering both diffusion of the samarium and the neodymium. So during the simulation, the samarium-neodymium ratio in the orthopyroxene is changing with time. So let's see. Oops. So let's see. These are the diffusion coefficients the modeling is based on. Samarium and neodymium and the OPX are very similar to each other. They're and faster. They're slower in the CPX and a little bit different. So they're, here, these are really recent results that GWA generated, and it is considering both of those, but we haven't focused on what the impact is of changes in the samarium-neodymium ratio. So Eli Block and Jiba Ganguly did a lot of work on this for lutetium-hafnium system, but here we were really focused more on what's happening to these neodymium isotopes due to the chemical exchange of neodymium between orthopyroxene and clinopyroxene, and the faster diffusion over the 143 neodymium, we presume. What is that going to do to the ages?
Okay, I have a couple of other questions. If Shumit will allow me to ramble on.
Ask 2 more, Igor, and then I have a couple more on chat here, and then we can come back to questions for Jim afterwards. But let's say a couple more from Igor, and then I'll take the 2 from the chat here, and then we'll move on to Rebecca, and we can come back as James.
Okay, so there's in terrestrial rocks, for instance, eclogites, there is the issue, which is a very well known among petrologists, that there occur retrograde reactions during the exhumation. So you may have a perfect ideal eclogite consisting of pyroxene and garnet, and then at some stage water comes in and you form retrograde amphibole on top at the expense of pyroxene. So it's been a work done by Glodny about 13 years ago about how to tell the age of a retrograde eclogite, which turns out to be younger than the unretrogressed, even if their temperature history is exactly the same, because the 2 rocks are 1 meter apart. So the point is that the retrogradation or the retrograde reactions are a very much faster way to promote the exchange of radiogenic strontium in an eclogite than is diffusion.
Yep. Yep. I'm not very familiar with that work, but yes, I think there are all kinds of ways to short circuit the diffusion processes and have faster exchange in real rocks, particularly terrestrial rocks.
Okay, and third and last, then if there is lots of time later, we can chat on, is the experiment by Labotka 2004, where they had a feldspar reacted, sodium feldspar reacting to potassium feldspar, and they measured the oxygen isotopic composition by having doped O18 reacting fluid as to promote the potassification of the starting albite. And what they observed is that there was a very sharp boundary in oxygen isotope ratios between the reacted and the unreacted feldspar. And then there was superimposed on that extremely sharp boundary, there was a very subdued or very narrow diffusive gradient. So what they concluded from the experiment is that they could estimate a diffusion coefficient which was several orders of magnitude slower than the reaction rate. It's American mineralogist Labotka et al. 2004. So that would mean that it's fun to calculate what Euler did, the diffusion coefficients. However, if you have retrograde reactions, Euler's measurements are not conducive to estimating the geologic history of that sample.
Yeah,
It's not a question, it's a comment.
Okay. So
now, this does not apply, of course, to planetesimals and CAI inclusions and iron meteorites because there was no water involved. Terrestrial rocks do.
Yep.
I'll take it at that. I'll just comment quickly on that this observation on feldspars is actually a very classic one back to a very classic work of Jim O'Neill. That was Jim O'Neill's PhD thesis back in early 60s, where even without measuring profiles, they made that observation, and the Labotka work actually then looked at the profiles and confirmed that. And that is something I'll come back to maybe as a part of the longer discussion after the two talks, but I'll just mention two comments that I have here. So one is from, before you go to the other talk, and hang on, Igor, because this would be a good one to carry on after the second talk, okay? So on the other, so Philip Ruprecht says that on the isotope fractionation effect, you are looking technically at a model age with a 2-point isochron. So that makes sense to see these with time shifts. However, in better isochrons with more minerals, this effect probably leads to a breakdown of the isochron concept.
Yep, I think that is probably true. And we could add in, more minerals here in the modeling and try to see that. It would be really easy to add a third phase with finite volume that had fast diffusion, for example. And we could probably, look at that with this. But I think you're absolutely right. You definitely could just break down the whole isochron that way, and that would be a very interesting thing to look at. I mean, more minerals could be added to the finite difference model as well with different diffusion properties. It just would become a lot of work and very slow, I think, at least on my computer.
Mm-hmm. So I think there are more questions, but I will wait on that till after the second talk. So, Aura, if you would hold on, we would get to your question on geochronometers and phosphates. I'll just maybe pick up David Dobson's comment quickly that regarding the troilite case, quite a few meteorites I've seen contain inclusions of different sizes? Could you use multiple modeling of different troilite inclusions to get better constraints on the system?
Yeah, no, they definitely do. And oh, yeah, I think you could. I think that is an interesting, idea to look at. One thing that I didn't talk about, but I mentioned here, is you can also get better constraints on the system by looking at the metal at different distances from the troilite. And that's a lot of work for the isotope geochemists to do, but Thorsten's group did do that. They, if I remember right, they made some measurements in the first like 0.5 millimeter section adjacent to the troilite, and then in another shell away from that, and then kind of random measurements further away from the troilite. And okay, sometimes, right, you don't know the three-dimensional geometry. Basically, they're doing these on a 2D section of a hand sample of a meteorite, and you don't know where the troilite is in 3 dimensions. So there's always that complication. But there was a significant difference in the isochron age between the ones closer to the troilite and the ones further away that that could be translated into an age difference. And that actually is really nice, because then that can be used, and it has relatively large uncertainties, but that can be used, that the age difference, to determine what, within pretty large bounds, what the cooling rate was without
Yeah, I mean, I think more geometrical constraints are always useful for anything to do with diffusion, actually.
Yeah, and I think that's kind of the issue, is that your model treats the metal as inclusions within an infinite sink. Well, actually what you have is inclusions of sink inside an infinite metal. So
exactly.
that's, yeah, I think.
Yeah, it's not, the model is not a perfect representation of the geometry.
I never are.
For sure.
But that's why we're here, to see how we can improve things and do things differently or better. So that's,
yeah, and essentially, I think it wouldn't be that difficult to change the model. Basically, for me, it's a matter of convenience to use, the model that I have, rather than, and have worked on for, made modifications to over the last like 20 years, than to do a whole new one with inclusions inside.
Yeah.
okay, so I'll stop the discussion now, but Jim, in the meantime, you can also look at the chat to see the questions, maybe come up with answers, and we will come back to all of these later. So let me get out of here and go to the second talk. So we have Rebecca deGraffenried. Rebecca did just finished her PhD actually a month or so ago in the University of Honolulu in Hawaii. Before that, she had done a bachelor's in University of Texas, Austin in 2015, which was followed by a master's degree at University of Alaska, Fairbanks in 2017. And then she went on to Honolulu to work with Tom Shee and Julia Hammer to do her PhD on a topic that part of which she'll be talking about today. She's also worked as a staff member of the EarthScope National Office in Fairbanks in Alaska. And she's studied different aspects of volcanic systems, including the role of phenocrysts in controlling, I guess, phase relations and degassing and things like that. And she's just arrived in Bochum for a short postdoc. And the reason it's short is because she's got the very prestigious NSF fellowship, which she'll be picking up in ASU with Christy Till later next year. So I just let Rebecca get started. Rebecca, it's all yours.
Thanks, Sumit. Share the correct PowerPoint. Right, so we're going to be switching gears a little bit here to talk about volcanic systems and looking at decompression rates specifically, using a relatively new technique that's just really started coming into usage which is using melt embayments, and I'll define everything as we go along. So the reason we're really interested in decompression rates is because it's one of the big drivers that controls volcanic eruption style. So for at least me, I usually work with the high silica systems, so rhyolites mostly. And for rhyolites, you have to have fairly slow decompression rates in order to produce these kind of nice effusive eruptions that are not quite as hazardous to anyone in the surrounding area. Whereas the really big explosive eruptions that really catch everyone's attention tend to have much faster decompression rates. And there's a whole host of other reactions and processes that are modulated by decompression rate, mostly because it controls the amount of time for these reactions to occur. So decompression rate is a really important process, and a lot of work has gone into quantifying decompression rate in all the different ways that we can try to get at decompression rate, since it's not something we can necessarily directly observe. All of our techniques have to come from some other method. And one of the really important processes that depend on decompression rate is magma degassing. And so the whole process of magma degassing starts with a magma that's down, stored in the crust, and it has a certain amount of volatiles dissolved in it. So water, CO2. For the most part, I'm going to be talking about water, but everything that I talk about can be applied to CO2 and sulfur as well. And at some point, an eruption is initiated and magma begins to rise through the crust towards the surface. As that occurs, there's going to be decreasing pressure on the magma, which is going to decrease the volatile solubility. So at some point, that solubility is going to decrease to the point where bubbles will start to nucleate, so that volatile is getting exolved into some sort of fluid or gas phase. And those bubbles that have been nucleated will grow and coalesce as this magma starts rising towards the surface, and it keeps rising and that pressure keeps decreasing. And eventually, maybe, there will be enough time for these bubbles to all form interconnected permeable chains and the gas can escape. And at some point, this thing will erupt. And one of the key drivers for the explosive effusive eruption style transition is dependent on the whole amount of time allowed for this process and the development of permeability and the escape of this pressurizing gas. So melt embayments are these little pockets of melt that have been trapped in crystals. What you're looking at here is a quartz crystal from the Bishop Tuff that has a very nice embayment, big and very visible. But these these melt pockets do not close off from the host melt like melt inclusions do. They remain open. And so during this whole magma degassing process, these volatiles like water, CO2, and sulfur can exchange with that melt as this process occurs and will eventually record this whole degassing process. So if we look a little bit more specifically at how this all works and how this ties with diffusion and decompression rates, we'll look at a schematic of a volcano and its plumbing system. And we see this crystal that's down in the magma chamber and it's starting to grow. As this crystal grows, it can either close off and form a melt inclusion, or it can remain open and form this melt embayment that we can see right here. And if we look at this initial time when we have the initial formation of the embayment, there is some consistent amount of water in both the melt embayment and the host melt. Now, once this crystal gets picked up by an ascending magma, there will be some amount of degassing that occurs. So there's vesiculation in the outer melt. And you'll notice very importantly that there is no vesiculation within the embayment itself. Part of the boundary conditions requires that there is a vesicle at the mouth of the embayment to help with the boundary condition of fixing that water concentration at the end of the embayment. So as ascent occurs and decompression occurs, there is some amount of diffusion of water into this vesicle as the solubility changes. And once this crystal has been erupted, there will be some diffusive concentration gradient that has been formed in the melt within the embayment that is then preserved in the glass. And we can go in and we can measure that later on once we've collected the rock. So some of the work that I've done has looked at some of these modeling assumptions that go into calculating decompression rates from melt embayments. And there's three main simplifications that I've examined. The first and main one is looking at approximating diffusion as 1D. These melt embayments are 3D objects. And so you would anticipate that they'd be impacted by the 3D geometry, but most models are conducted as 1D diffusion models. A lot of, actually, I think every single other diffusion model also assumes that there's equilibrium degassing, so that at each pressure step, the corresponding change in volatile concentration is what you would expect based on solubility relationships. And finally, I'll also look at the assumption of isothermal decompression. But for the purposes of this talk, I'm going to focus purely on the geometry concept here. And I'm going to be showing some results that I've recently published, and also look at the extension of those results to show some new stuff that I've been working on. If you're interested in those other two aspects, there is the paper that you can go and look at, or I'm happy to discuss it with you at the end. So looking at the geometry, one of the really key aspects of geometry that I examine is this constriction at the opening where the embayment meets with the host melt. So this big green square here is going to be the host melt, and then this is the embayment itself. And so I range how much I constrict the opening of the embayment to what we would consider a cylindrical geometry where there is no constriction, all the way up to something that has an 80% constriction. So the way that the model works is we're looking at Fick's second law, and we solve it numerically either in 3D or 1D. So the way that my modeling worked is I would first run a diffusion model in 3D, and then I would pull a profile from the very middle of that 3D matrix of concentrations. So pretending that I had some embayment that I was polishing through, and then I went and measured a profile from the middle of that embayment. And then that 1D profile, I would then fit with a 1D model and look at whether or not this 1D model could actually recreate the known 3D rate that I imposed in my initial 3D model. So here I use the diffusivity dependent model, where the diffusivity of water, which was my volatile of interest, is dependent on the concentration of water within the melt itself. So even though we have our second derivative, at least in the first partial derivative, diffusivity is included in here. However, melts are quite nice because diffusivity does not depend on direction. So it's the same diffusivity for all three terms here. So I use a centered finite differences solution. And in order to prevent any water from diffusing into my crystal, I imposed fictitious points to help with the no flow boundary there. And essentially these fictitious points would reflect back any flux that was going into the crystal. Now that does give the inherent assumption that decompression was fast enough that there was no significant water diffusing into the crystal itself. And then we have our diffusivity and solubility equations to round it off. So to look at these results, on the plot here, our x-axis is the known decompression rate, and the y-axis is the modeled 1D decompression rate. So these different lines represents a different geometry, ranging from cylindrical all the way up to this 80% necked. And what we can see from this plot is that as you constrict that opening, there is a pretty significant impact on that 1D model decompression rate. And it's very nice visually to see it this way. But if you really want to know, okay, well, by how much is this 1D model overestimating the actual true rate, it's a little difficult to tell from this plot. So I'm introducing this term called a decompression rate multiplier, which is essentially just the ratio of the 1D decompression rate to the 3D decompression rate. And if we want to think about it in terms of something useful for a modeler, you can think of it as what you would need to divide your 1D decompression rate by to then retrieve the actual true 3D decompression rate. And it also just makes it easier to visualize the trends. So if we now look at another plot, we have now just the modeled 1D decompression rate on the x-axis and this decompression rate multiplier on the y-axis. And it shows this interesting trend of at very fast decompression rates, we're more or less retrieving the correct decompression rate regardless of geometry. But at some point we start really rapidly increasing this decompression rate multiplier, and then it'll hit a maximum and then start to decrease. So this is kind of an interesting trend here. But the main takeaway is that some of these geometries are really quite problematic, and you can start to introduce some fairly significant errors. Some of these are over an order of magnitude into your calculated decompression rates if you're trying to use these 1D models to represent these more problematic geometries. However, that's a bit of a problem if we're starting to eliminate usable embayments, or if you have to start adding in a lot more analytical or computational work, because it's really a problem of numbers for trying to actually say something useful about the dynamics of particularly big volcanic eruptions. So here's an example from Myers et al., who just recently used melt embayments, which are these triangle data points here, and bubble number density, these circle points here, to measure variations in decompression rate for the Bronze Age eruption of Santorini. And this requires a lot of embayments. We have multiple phases of the eruption, and for each phase of the eruption, you have to measure multiple embayments. So it really requires a lot of embayments to do this kind of work. But we already have a restriction that we can't have bubbles in our embayments. We have to have these bubbles at the mouth of the embayments in order to really be sure of our boundary conditions. And now, if we have to eliminate certain geometries or have to start working in the world of 2D modeling and 2D mapping of volatile concentrations, that really starts to add a lot of work to using this technique, which is not great for something that you want to be able to use regularly. So with these 3D models, we can actually start to target the things that are influencing this decompression rate multiplier and then correct for them so that we can still use the really nice 1D models that are very simple, computationally not very intensive, and analytically much easier to work with. So we can look at these 2D slices here. This is the cylindrical geometry, and this is a 60% necked geometry. And this is at the end of two different decompression runs. One is 6 megapascals per second, and one is 0.1 megapascals per second. And you'll notice that the neck of the embayment causes a bend in these water concentrations. So these lines here are marking out contours of water concentration. And this is what's actually causing the increase in the decompression rate multiplier. So our cylindrical embayment did not show any increase. It doesn't have a neck, but our necked embayments have a neck, hence the name, and they did have an increase in decompression rate multiplier. And it's based on the neck is influencing the shape of these water contours. So we know that the neck is tied to this increasing decompression rate multiplier. But then the decrease, which very slightly happened in the cylindrical embayment and also in the necked embayments, we can actually attribute to the back of the embayment, where the curvature of the back of the embayment then produces this opposite curvature as compared to the neck, this opposite curvature in the water concentration. So we know that if we're trying to correct for these things, we need some sort of influence of the neck, some sort of influence of when diffusion hits the back of the embayment. And all of this is most likely going to be tied to the diffusivity of whatever species of interest that is being modeled. And then also the width ratio of this neck. So we know that the magnitude of that decompression rate multiplier is also very strongly dependent on just how constricted the embayment is. As we increase that in constriction, we are increasing that decompression rate multiplier. So the question becomes, how do we fit this trend? Well, we'll take an example from the 60% neck geometry. What we have plotted here is this 1D decompression rate and the decompression rate multiplier. And these green points are all of the modeled data points. And the dashed line is actually a normal distribution. This is probably not using a normal distribution correctly, but the shape of the equation actually works quite well for modeling the behavior of each of this whole suite of models. And I'll be using that term, a suite of models, to refer to a set of 3D, 1D models that all use the same geometry, same diffusivity, same geometrical parameters, but vary in 1D or vary in the imposed decompression rate. So we can use this normal distribution equation, and we introduce these terms, this multiplication factor, because you'll notice that we don't stop at 1 like a normal distribution would. And our baseline is actually 1, so we have to add 1 to then bump it up. So you'll notice this starts at 1, and our normal distribution here will actually tail off to 1. So the problem becomes, we needed to find functions to define this multiplication factor, the sigma mu, because in this case, x is going to be that 1D model decompression rate. And we want to be able to spit out this decompression rate multiplier, so then we can correct this 1D decompression rate and back out what was actually the true decompression rate, taking into account the 3D geometry of the embayment. So the main parameters that we are varying here is so if we look at the embayment neck and the embayment body, we have the ratio of the neck width to the embayment body width. We also have to account for the length of the embayment neck, because that's going to define how long it takes before that decompression rate multiplier starts increasing. Then we also need to account for the length of the embayment body, because that's going to change when that decompression rate multiplier starts coming back down. And all of this is going to be tied to diffusivity, because that's going to control how fast all of this is happening. And we're trying to keep things in terms of diffusivity so that it is independent of whatever volatile someone wants to measure. So I'm creating all of these using water, but it should theoretically work for other volatiles as well. So the way that this strategy works is we have these 4 parameters that we know we need to figure out some sort of fitting method for. And so we're going to need different model suites that vary each of these parameters. So for example, with diffusivity, we can have a slow, an intermediate, or a fast. There's actually more than that, but so that this doesn't become a gigantic plot, we're just going to say 3 for each. So for each of these, we're going to run a suite of models. I've been doing at least 6 per model suite, though sometimes it requires more if the relationship is complicated. And so with each of these, there will be some sort of multiplication factor, sigma and mu, that will best fit that one model suite. So this quickly becomes a very cumbersome thing. So just to give an example here with the diffusivity, so there are 4 diffusivities that were run. Each data point is a separate 3D and 1D model. And each of the dashed lines represents a best fit distribution that fits the data. And so each of these lines represents one unique multiplication factor, one unique sigma, one unique mu. Of these, then we want to define a function that can account for the variation in each of these as a function of, say, diffusivity or the width ratio or the length. So there's a lot of different functions that we now have to try to fit. So we can look at the overall shape of how, say, the multiplication factor varies as a function of diffusivity and how sigma varies as a function of diffusivity, and so on and so forth. There's several functions here, and all of those might have different shapes depending on how each parameter influences how that curve gets shifted or how the magnitude of the decompression rate multiplier is impacted. And so finally, once we have the shape of all of that, we can then derive a best fit equation. So there should be some kind of equation that describes how the multiplication factor varies as a function of diffusivity, the width ratio, the length of the neck, and the length of the body. So we have 3 independent equations that we've then derived based on all of these model fits. And so what I envision a user doing is you would have these different parameters that you would measure from some embayment. You would plug them into the equations. And for your embayment, you would have a multiplication factor, a sigma, and a mu that you calculate. And then you take the 1D decompression rate and you plug all of that into that normal distribution equation that I showed earlier. And that would give you the decompression rate multiplier. You would then use that decompression rate multiplier to correct the 1D decompression rate to what the true decompression rate should have been if, say, you had used a 3D model, which is not ideal for any sort of practical purpose. So if we look at the current state of the correction factor calibration, it's not doing too bad. There's a lot going on in this plot, so I'll step you through it. The decompression rate multiplier from the diffusion models is on the x-axis, and then the decompression rate multiplier from the correction factors is on the y-axis. And the colors correspond to what's being varied. So the red symbols are all just purely for how constricted the neck is. The blue colors are for varying the length of the embayment body. The green is for varying the diffusivity. And then the yellow points are the non-calibration models that succeeded. The black line here shows a perfect one-to-one retrieval. And then the 2 dashed lines just show plus minus 10% of the true value. And that's really what I'm trying to get at, is to have most of these to be retrieved within plus minus 10% of the original value. For the most part, these are doing quite well. And so all of these are the calibration models. So at least the calibration is doing a pretty good job of recreating the models that were used to calibrate it. That's always a good thing. There are a few problematic spots still. So those 2 points there are from the very low diffusivity, and they're still not quite fitting in well. And that shows in the non-calibration models that fail. So I don't have those plotted on this plot right now, because they would plot kind of somewhere down here, because when it fails, it gives some sort of like negative number. So we know for sure it's really not working. And that's actually, the lower diffusivity models are actually the ones that are failing more frequently. But the successful non-calibration models are working quite well for a diffusivity of greater than 35 microns squared per second. And as long as the shape parameters are also within the calibration, it's working pretty well so far. So some of the needed improvements here. I have done a lot of 3D models. So right now, all of that data represents 70 3D models and then corresponding 1D models. So it's a lot of computation work going into it. However, the calibration for slow diffusivity is not quite right. So that needs some fine tuning, potentially even more model suites as well. And then also the calibration for the various length parameters needs some work, and that's probably going to require another 3 to 4 suites, maybe more, depending on how well it works. Because what I would really like is for these to be very broadly applicable to any sort of embayment that a researcher might come across, and really make sure that people can still use the 1D models. However, there are a few limitations, and one of the main ones is that some of the embayments have some really complex geometries that involve curvature, and this will not be able to account for curvature. If you want to use a curvy embayment, probably still going to need to use a 2D model. Maybe at some point I'll try to tackle curvy embayments, but for right now it's already quite a task in just getting the neck constriction down. And then these also require a fairly simple degassing pathway. So it's assuming that there is always diffusion occurring, no stalling, where there's no diffusion occurring, no degassing occurring. So it has to be a fairly simple degassing pathway. But hopefully that's not going to restrict things too much. But I will be happy to take any questions that anyone has about this right now.
Thank you, Rebecca. So that's a good introduction to the embayment system and all the issues that can come up with that. And I'll look for questions. I'll give you a minute to catch your breath. And yeah, I have one for you from Mike Yolans. Hi, Mike, first of all. And have you looked at the accuracy if you trace over an embayment shape in a photomicrograph and run a 2D model?
Yeah, so it's actually something that I've tried to do with some natural embayments. So when I was actually creating this whole diffusion model, we were having to work hard to make sure that it would be applicable also to non-symmetrical embayments, because it's very easy to have the boundary conditions correct for something that's beautiful and symmetrical. But once you run into natural embayments, those are very not symmetrical. And so we want it to be applicable to natural embayments. So I haven't tried anything with 2D to 3D comparisons, but it should work fine. I've only used them on natural ones, so there's not a way to really test whether or not it's accurate.
Okay, so you have a few comments from people who complimented you on your talk, so it's a nice talk. There's a question back to that from Jim. He says, under what circumstances would the slow diffusion inaccuracy apply? Low water content or sulfur, or where do you think it becomes important?
Yeah, so at least in my calibration models, the way I'm getting some of the slower diffusivities is for a shallower storage pressure. So I've started those at about 110 megapascals, which that's honestly not outside the realm of possibility. So some of these more shallowly stored magmas could have slower diffusivities. And then certainly CO2 and sulfur are going to have slower diffusivities than water. But I still want this to be useful for CO2 and sulfur diffusivities as well. So do actually have to solve that slow diffusivity problem.
There are other questions, but I have a related one myself, so I'll just throw that in. So seems to me like the solubility should go into this calculation somewhere as well.
Solubility is in the actual calculation of the diffusion model.
Right.
So at each time step, I'm resetting the outside melt to be the solubility value.
Right.
And that's what it's exchanging with.
Right, and because that defines the gradient under which it's diffusing, seems to me that that should be another parameter in addition to diffusion rate that should affect how it's changes on different essentially.
Yeah, so that's accounted for in just how the model itself runs, because you have to reset what the outside melt water concentration is at each time and pressure step. You don't reset it inside the embayment. It's the melt that it's exchanging with. So you have to define a degassing pathway with that as well.
Seems to, well, we can check into that, but I'll just get to the other questions here because there's a lot coming in. So David Dobson says the low diffusivity problems are surprising since those simulations might be expected to have the diffusion contained within the neck. So be closer to a ratio of 1. Do you have any feeling why these aren't working?
Yeah, so I can potentially answer that with this plot here, because this is actually the different diffusivities. So it is true that it takes a while actually for there to be any sort of impact on the decompression rate, because you'll notice these two here are already pretty close to 1. It takes a while for that to actually start to show any sort of impact from the neck to geometry. And I think it's probably a bit poorly defined. You'll see that it's kind of sharp and jagged right here. I think I need a few more runs in here to better fit the curve. And so that probably is part of the problem, is that there's just not a model right here to help define that curve a little bit better.
Okay. So Mike Yollens has a follow-up question. So Mike, are you in a position to unmute yourself and maybe show yourself and have this discussion? Because I can read it out, but
yeah, no, I'm here.
Yeah, so go ahead, Mike.
Hey. Yeah, so we read this paper in our reading group here, and there were a lot of questions that we need to ask. But it was kind of like a dream, the idea that you could just take a photomicrograph and just draw a picture, trace around it, and then do the model directly, and then you don't have to worry about all of these parameters. It would be all solved. But and it would be 2D as well, so it would be considerably faster. But yeah, so the other thing was, do you have to think at all? Do you think about the hydrogen moving into and out of the olivine through the host mineral at all? Is that
so
worth looking at
least for the way the model is structured right now, we're assuming that decompression is fast enough that any sort of diffusive flux into the crystal is essentially negligible compared to the amount of diffusive flux moving down through the embayment towards the opening, at least. Potentially for slower decompression rates, that could be a problem. And I would have to kind of redo the model and allow for diffusive flux based on some sort of distribution coefficient and see where that turning point is. That's certainly something that could be done and probably should be done.
Yeah, awesome, thanks.
Yeah.
Okay, so then I have a question from Francois Holz, who asks this regarding the solubility value. Do you assume only water as a fluid phase that is degassing? In other words, are you assuming water saturated conditions?
Right, yes. So at least for simplicity's sake with these calibrating models, really only focusing on water. It is possible to model several elements in the model itself. So you can do multiple phases degassing. But for right now, to try to really nail down the different factors, I've mostly simplified it to just water. But because everything is based on diffusivity, not anything related to a specific element itself, it should be broadly applicable to any sort of volatile species, provided that it fits within the calibration bounds.
But again, it'll relate to the boundary conditions changing very differently if you have different volatiles.
Right, right. And so some of the problems might crop up with the sulfur and CO2, because those might actually be ones where they have very complex degassing pathways. And these might not work as well if the degassing pathway is too complex.
Right. And Jim has, again, a follow-up related question, which is, if I understand the boundary condition at the opening, you assume a bubble is present there to fix the volatile concentration there. Is that common in real embayments? If it were not there, you'd have a more complicated 3D problem, I guess.
Right, yeah, and at least the people who publish these studies are all very good about making sure to show that there is actually a bubble at the mouth of the embayments, or at least there is an indentation into the melt that is preserved that is presumably the location of where a bubble used to be. So as far as I have seen in the literature, people do actually follow that condition pretty rigorously.
The question is, how common are those? If you have 10 embayments, how many of those are likely to have a bubble in front of them?
That I don't know. I guess it's not such a big problem that it forbids using embayments entirely. It is a little bit problematic because most embayment studies don't have quite as many embayments as I think should be used, but studies are now moving towards using more and more embayments to get better statistics on decompression rates. So they exist, they're out there. It may just take a lot of searching through crystals to find that perfect embayment. So that's why having geometry not be a limiting factor is nice.
Yeah, I remember when the first of these were coming out, people told me that they'd spend a lot of time looking for the right embayments.
Yeah.
So then there's a question from Alan Lerner who's saying, do the 1D models assume a slice is taken through the center of the embayment? From a practical measurement standpoint, it is probably rare for opportunistically intersecting embayment to be explored right along the middle. So what do you do about that?
Right, yeah. So this does kind of assume that you've crushed up your sample, you've got your crystal very nicely aligned, and you're very careful with your polishing, and you section it right perfectly through the middle. Whether or not that is something that any reasonable human can do multiple times, that's up for debate. And that's also something that would be an interesting side study as well, is to look at sectioning effect. So I know they've done a lot of sectioning effect studies in crystals, and it's a big problem in crystals. So I would assume that it is a problem in embayments, but this is sort of taking it one step at a time, and that's definitely a future place to look, is looking at sectioning effects.
Mm-hmm. And then I have Aura Cuervo, and she has there's a question for both of you, actually. She had a question earlier for Jim. So I'll ask you first, and then I'll go back to her question for Jim. So the question to you, Rebecca, is what advices do you have to identify melt embayments in samples of phosphates?
Yeah, that's tricky. So at least olivine and quartz are nice because they are transparent. And at least olivine, if you get it small enough, is relatively transparent. So you can actually spot them just with a reflected light microscope. Phosphates, I guess you would have to hope that you could see through it well enough. I'm trying to think. I don't know if I've seen anyone do like an apatite embayment study.
I don't know. Alex is around here, but she has looked at apatite, and I don't know if she has any thoughts.
Yeah, because I know I've seen plagioclase used, and I've seen embayments in pyroxene in thin section, but that I don't know how you would spot it from the outside. You would have to just polish through the crystal and hope that you found one, which is not a great strategy if you're hoping to still use that mineral for something later on.
Yeah. And so I'll take her other question to Jim now.
Yeah. Should I stop sharing my screen?
Right. Well, you can stop sharing your screen.
Okay.
So the question for you, Jim, from her was, what advices do you have to evaluate changes in the closure temperature due to the effects of partition coefficients of geochronometers in phosphates?
Yeah, so that's a good question. It would depend on what system you're looking at. I'm not that familiar with phosphate systems. You know, I know that they're used. I'm more familiar, I guess, with meteorites at this point, but phosphates are often used with, you know, uranium, lead, dating, lutetium, hafnium. But it would just depend on what particular system that you're looking at, and I'd be happy to you know, talk with you more about that. You know, if you want to shoot me an email and you have a particular situation that you're looking at, you know, it'd be fun to discuss.
So then we can go back to Rebecca, and David Dobson says, can we assume that the best estimate of from a study of multiple embayments will be the slowest decompression rate? Is that always the case?
Yeah, so actually a big problem is that crystals are not always sourced from the same place or the same depth. And so even within the same package of magma, you might have crystals that started out at a much greater depth that then start degassing earlier. And if their initial water concentration is different from other crystals hosted around them, there might be problems associated with assuming what water concentration you started with. And then when you then calculate the decompression rate, that might also be impacted. So I think getting more embayments studied helps kind of constrain this factor of uncertainty of where actually the crystals themselves were sourced. And that will impact your decompression rates.
So, but is there a trend that you see that the slowest ones are the ones that are most realistic or something?
I don't know if there's enough out there to really say anything definitively. I mean, so the study by Madison Myers that I showed an image from was that the embayments are certainly recording a slower decompression rate than, say, bubble number density. But that makes sense because bubble number density should be recording essentially the fastest part of decompression, whereas embayments are an integrated decompression rate. So what that decompression rate is integrating could be different for different crystals.
So the related question I have is, did you try doing a 3D correction on her data and see what it does? Does it change much or?
No, I haven't done too much with Madison's natural data. I've worked with her a little bit on some of her stuff. We were actually going to do a very detailed study with this, with her Yellowstone embayments, but then COVID happened and that kind of fell through. And we have not picked it up since then, unfortunately.
Life under COVID, indeed.
Yeah.
Okay. And so I have one final question for you. Are you planning to put this code available for people somewhere or something so people can use this?
Yeah, eventually we'd like to get this published as an actual usable code. There are a few more. There's a new one that just came out actually that is a freely available software already that does 1D diffusion. And I believe that one also does water, CO2, and sulfur. Okay. I can't remember exactly, but there are starting to be codes out there available for use. At least the 3D one, I think, needs some serious cleaning up before people can actually use it. It's not the most intuitive thing.
So that's a good point for me to announce something. So what we also plan to do is to have a website where we almost have the website and start putting available models for diffusion in there. So people who are interested in using things can go and look in one place, you know, what's available and things. So if any of you out there have codes that are available that are published somewhere or, you know, have something to offer, just drop an email and, you know, tell me if it's already there on a website or in a particular publication where it's available, and we'll try to collect all of those in a web page so that it becomes a good resource for people to do that. So with that, I think No, we haven't stopped. So we have more questions for you, Rebecca. You're not off.
Oh no.
So more compliments on your talk, but the question is, I'm not sure if you have already talked about this, my audio cut out, but I have a question regarding the assumption of equilibrium degassing. Do you think if CO2 and maybe also sulfur are incorporated into your models, you might find that the equilibrium degassing simplification may become more complex, particularly for faster decompression rates where slower diffusers like CO2 might not keep up pace?
Yeah, so that's where modeling them all in conjunction with each other is really useful. The equilibrium versus disequilibrium is more related to when vesicles actually form. So at least in terms of how I model disequilibrium degassing, it's more related to when the vesicles themselves actually form. So it gets into the whole problem of heterogeneous versus homogeneous bubble nucleation. I'm more familiar with that with water. I'm not sure with CO2 and sulfur if anyone's done any studies about particular bubble nucleation related to that, but certainly CO2 and sulfur will not start degassing without a bubble of some sort present, though usually that bubble would be predominantly water. So that is part of the limitation that I've mentioned with the complex versus simple degassing pathways. And the equilibrium is kind of necessary for these correction factors to work, because they do assume that there's constant degassing, that then the diffusion front is constantly moving up into the embayment.
Yeah, I mean, it's the question of mixed volatile partitioning that Francois was talking about earlier as well. That will become really quite critical in this thing.
Yeah.
So yeah, the questions we have just about at the end of our time, but I was going to see if Igor wanted to pick up the issue with feldspars again with Jim.
Yeah, hi. I mean, this could go on forever. One thing that I did not mention is that the big deal about feldspars is that a paper just came out in chemical geology that the structure of the feldspar is not remaining neutral. So when you have a feldspar that changes its structure, I'm not sure that there are any diffusion equations which account for a variable matrix. They account for variable boundary conditions, but not for a change in structure, especially in the opening of the tetrahedra ring. So we're modeling something, I mean, the usual, the Crank-Nicholson is assuming that the structure is neutral, inert, and there is one lone atom moving around the place.
That's generally true. And there are models of diffusion with phase transitions, but I don't know that much used in geology. So.
Well, that's I mean, that's the rub. I mean, we can model things, but they may not be representative of the real world.
A feldspar, perhaps, yeah, but you know, there are not all the minerals all the time have phase transitions. So
oh no, don't get me wrong. I'm not saying that there is no diffusion. We've had the discussion many times, and there is always diffusion, not never, but the contrary. There's always some. But the problem is, what is the fastest process that happens in a real rock? And this
right.
is
the thing that I want to bring up in context of the closure temperatures is that, I mean, yes, if you have any form of dissolution precipitation that affects things, the same thing happens also with melts actually. So melts and crystals and phenocrysts have so my perception is that we need to move towards reaction diffusion models, because once you do that, then like you said, there are very steep diffusion profiles. Those things happen as a part of the reaction diffusion model, and that's something we really should be, the next generation of our models should be looking into more of those. It's my kind of take on that. I don't know. Jim, David, anybody here? Thoughts?
That's just my comment, as I tend to go toward things that are simple, that because there's so many things that we don't know, you know, there are so many complications in a lot of systems that we don't have experimental or, you know, kind of theoretical constraints on. So I don't know, that's just my own personal thing, I guess. It's just migrate toward things that are a little simpler.
Yeah, I mean, even in something simple like where you're just dealing with dissolution of minerals into melts, suddenly you've got so much extra things to consider, haven't you? You know, the kinetics of the detachment, let alone anything else, as well as the diffusion. So as soon as you get into coupled diffusion and reaction, there's so much more complexity.
Yeah,
even in simple systems.
Yeah, I mean, I look at all the papers on dissolution and growth of calcite, and there's just, you know, an entire encyclopedia on just that, which surface of calcite dissolves in what way.
Yeah.
So yeah, one can do a lot. But that's good for all the people here. They have work to do for the future.
Yeah, I'll see my career out anyway.
Yeah. So I don't see other questions, and we are actually smack on the time. So maybe I'll thank everybody for being here. Before I sign off, maybe I'll give Linda to announce the next talk and if she has any technical comments on what you can do. So I'll sign off. Thank you, everybody, and see you in a month or so. And Linda, it's yours now.
Yeah, thanks everyone for joining this meeting today. I just have a last announcement for today. I'm just going to share my screen. So for the next meeting, we have two talks, one from Yuxo Zhang from the University of Michigan, who's talking about multi-component and isotope diffusion in silicon melts. And the next talk from Hannah Shamlu, Oregon State University. She's talking about magnesium diffusion in Sanidyne experiments. And this talk will be on 23rd of September. Yeah, and I hope that a lot of people will join again. Okay, thanks everyone for joining today, and see you next month.
Thank you. Maybe very quickly drop Linda or me actually a mail if you want to be on a mailing list. So whenever we have new talks, you know, you can get an announcement automatically, and we hope that you keep coming back. Thank you.